In this presentation, I'll be explaining single phase fully controlled rectifiers. Now let us see a single phase fully controlled rectifier with resistive load, R load here. Therefore, this is the topology of circuit diagram in which a single phase applies the, and this is the load R is the, and this is the bridge rectifier in which here there are four thyristors, T1, T3, T2, T4. During the positive half cycle, here a T1 and T2 are getting fired, and during the negative half cycle of the input, T3 and T4 are getting triggered. Therefore, here during this is the input voltage waveform. 0 to pi radians, the input voltage is positive. Here is positive with respect to here, and from pi to 2 pi radian, here this is positive with respect to this one. Therefore, during positive half cycle, this is getting forward bias. Similarly, since it is negative, this is getting forward bias. Or T1 and T2 are getting forward bias during the interval 0 to pi radians. And from the interval pi to 2 pi radians, you can say that one the voltage at this point is negative or this voltage is positive. Or since the voltage this is positive, T3 is getting forward bias. Similarly, since it is negative, T4 is getting forward bias. Therefore, from 2 pi to pi to 2 pi radians, here T3 and T4 are getting forward bias. Therefore, this can, if you are triggering this T3 and T4, that will be conducting. Now again coming back to here, at firing angle from 0 at a firing angle alpha here, that is from 0 to pi radians, that one the input cycle, it is fired at an angle alpha here. Once it is fired, T1 and T2 are fired at an angle firing angle alpha degrees. Here you can see that once it is conducting, we are assuming that it's like a closed switch, because they are assuming that forward voltage drop is 0. It's an assumption. Therefore, once it is switched or T1 and T2 conducts here, the circuit diagram is like that one. From the source input here, T1 conducts, and through the load it is coming back. Then it is returning back to T2 and it is coming to here. Suppose circuit diagram is this one, or you can say that one, the output voltage is same as the input voltage. The path is like this one. Output is voltage is same as the input voltage. That is why here the output voltage is same as the input voltage at firing angle alpha, same as this one. At pi radians, inputs here the current, the voltage is reducing to 0. The input voltage is reducing 0. Therefore, the current through the device T1 and T2 that gets reduced to 0. Here can say that this is a current waveform. Current is reducing to 0. Once the current goes 0 here, the device is getting turned off, because once the current flowing through the thyristor is going less than the holding current, that thyristor gets turned off. Therefore, at this instant, the device is both T1 and T2 gets turned off, and T3 and T4 is forward bias in this from pi to 2 pi, but that will be fired only after alpha from pi radian. So from the pi or pi plus alpha, that is fired. T3 and T4 are fired at this instant, or from here if you calculate, it is equal to pi plus alpha. For pi plus alpha, both T3 and T4, they are forward bias and they are getting fired. So once T3 and T4 are fired here, in that during the negative half cycle, you know that this is equal to positive and this is equal to negative. Therefore, T3 is positive, or that's getting forward bias, and T4 is also, since it is negative, cathode is negative, that is getting forward bias. Therefore, in that case, the path is like that one. Since it is positive here, it is coming to T3 and again returning back to load R, and then coming to here, and then coming to T3, and it's returning back to this one. Therefore, again the current through the load is same direction, always from the upper to lower, and the voltage is, we can say that one, the voltage is same as this voltage at this point. Therefore, it is equal to, again this is just inverted, and the voltage will become, since current is always here, he will be getting a positive voltage. Therefore, the voltage across the load is again, it is positive, and again as 2 pi radians, the current through the devices which are already conducting T3 and T4, that is reducing to less than the holding current, that gets turned off. Here T3 and T4 are getting turned off, and again 2 pi plus alpha, that is repeating. Therefore, from alpha to pi, T1 and T2 are conducting. From pi plus alpha to 2 pi radians, T3 and T4 are conducting. Therefore, this is the output voltage waveform, voltage across the resistance, and the current is given by voltage divided by the resistance, which is the same as in phase to that voltage, and this is the source current. If you see the source current form here, you can see that one. The source current is when T1 and T2 are conducting, the current is in this direction, flowing in this direction. But when T3 and T4 are conducting, we can say that current is like this one, and through this one is the same direction. But returning, you can say that the current through the source is getting reversed. It was earlier, it was like this one, 0 to pi. For pi to 2 pi reading, it is the reverse. That is why the input current, we can say that it is like this one. So this is the input current. This is, or input current means source current. This is the output current. This is the output voltage, and this is the input voltage. Now let us see the average value of the output voltage as well as RMS value of the output voltage. Here, in order to find out the average value of this output voltage, instantaneous voltage is given by Vm sin omega t. Average voltage is given by 1 by pi integral alpha to pi, that is Vm sin omega t. Therefore, we are actually, this area is calculated, that is spread over pi radians. That is 1 by pi integral alpha to pi Vm sin omega t d omega t, or it is equal to minus cos omega t, that is integration alpha to pi, or Vm by pi outside, or Vm by pi into 1 plus cos alpha. Therefore, the average value of this voltage is given by Vm by pi into 1 plus cos alpha, where alpha is the firing angle. Now coming to RMS value of this output voltage, RMS value of the output voltage is equal to square root of root mean square value. Root of mean means 1 by pi. This to be calculated 1 by pi. Square of the output voltage. Vm square sin square omega t d omega t. Of course, the range is equal to alpha to pi. Alpha to pi. Therefore, if you are integrating this square of this voltage over alpha to pi, and that dividing by pi, will be getting mean, and again taking the root. It's called root mean square value. And if you calculate that one, square root of 1 by pi integral Vm square into sin square omega t equal to 1 minus cos 2 omega t divided by 2. That integrator, d omega integrated alpha to pi, then we'll be getting Vm by root 2 into square root of 1 by pi into omega t minus sin 2 omega t divided by 2, or the RMS value of this output voltage, that is, this is the output voltage. RMS value of this output voltage is given by Vm by root 2 into square root of, you substitute this limit here, pi minus alpha plus half sine 2 alpha. That is the average value or RMS value of the output voltage. And the average value of the output voltage is equal to Vm by pi into 1 plus cos alpha. Of course, form factor is given by RMS value of the output voltage divided by the average value, or VRMS divided by VDC is the form factor of this output signal, output voltage. Now, if you consider an inductance in series to a resistance called RL load, previously we considered only resistance, but if you consider an inductance here, and here the effect is that again it is fired at an angle alpha, that is when it is fired in, that is T1 and T2 are conducting here, and here because of this inductance, that is because inductance has inductive voltage, that is when current is, of course here the can say that current is increasing, current is not reducing to 0 at this point. Previously it was 0, but when voltage was changing in purely resistance case, but here because of the inductance, inductive energy stored here, again a current will be continuing to flow in the same direction, and because of that one there will be a voltage across it that will be forward biasing this SCS, which is already conducting. Because of this one, that is because of the inductive voltage across the inductance, even though the input voltage is going negative, this voltage adds up with that, so that again it will be in conduction state. That is why here you'll be getting the output voltage is same as the input voltage even after the voltage is going negative, because of the inductance still the T1 and T2 gets conduct, and the output voltage is same as the input voltage, that is going negative. Once the inductive energy is over, the current will become 0, and current becomes 0. Once the current becomes 0, here the T1 and T2 gets turned off, and here and the thyristors T3 and T4 is turning on only after alpha degree from pi radians, therefore only a pi plus alpha only. Until that point, that is from beta to, this is called the beta angle, that's the instant at which until the current is current is non-zero, that is the beta, and from beta to pi plus alpha, none of this thyristor is conducting, therefore the output voltage is equal to 0. Therefore this is actually a discontinuous conduction case in which there are 0 current instants, that is here during this period current is 0 and the output voltage is 0. Again, during the negative half cycle of the input, that is from pi radians to 2 pi radians, as I already explained in the previous slide, T3 and T4 are getting forward bias, because here you'll be getting positive and here you are getting negative. Therefore, T3 and T4 are getting turned on, or that's forward bias. Therefore, you can trigger at the pi plus alpha T3 and T4. Therefore, the conduction like this one, again the current is flowing like this one, is returning back to this one. Therefore, here you can see that one, again the current is positive or the same direction here, and during that period the output voltage is same as the input voltage. Therefore, again, of course, here the output voltage polarities of reverse actually. Here the input voltage equal to plus and here equal to minus during the negative cycle. Therefore, that is why the polarity now reverse in this case. Rather than, though it is a negative half cycle, the output voltage is positive because the current polarity of here is positive. Therefore, the output voltage is again here, and that is repeating, and that will be continuing because of the inductance. Even though the voltage magnitude is 0, still it is continuing. This continuation of this one, that is because of the inductance or the inductive energy. I mean, that energy, that will be that voltage across the inductor, that is still forward biasing the SCS, which is already in conduction, and because of that current continues. But once that energy is over, here that current goes 0, and then until the next firing, voltage equal to 0, and that happens. That will be repeating. Therefore, in this case, the current is not continuous; it's a discontinuous conduction. But if you increase the magnitude of the inductance, then you can get a continuous conduction. That depends upon the value of the inductance that is in series to the resistance. If R is very large, you can get a continuous conduction. But this is an example in which shows the discontinuous conduction. Certain region, the output current equals 0, and when output current equals 0, none of the thyristor is conducting. The output voltage is same. Sorry, output voltage equal to 0. And when any of the two thyristors are conducting, we can see that one here. When T1 and T2 are conducting, output voltage is same as input voltage. When T3 and T4 are conducting, of course, output voltage, of course, with an inversion it is coming. This is the output voltage. Therefore, this is the output voltage and this is the output current. And the input current, as you see that one, during positive cycle, the current is in this direction because T1 and T2 are conducting. And during the negative cycle of the input, T3 and T4 are conducting. Therefore, in that case, the source current is opposite direction. That is why source current is opposite. And this is the load current. And this is the load voltage. And this is the input voltage. This slide represents the same what I already explained in the previous slide. Therefore, here during the positive cycle, T1 and T3 is forward blocking state. But I mean, in that case, we can turn on at an angle alpha, because the forward bias case, it can be turned on at omega t equal to alpha, at T1, T3. And at omega t equal to pi, T1 and T2 continues to conduct due to the stored energy in the inductor. Because of the energy stored in the inductor, that still continues to conduct. At omega t equal to beta, that is until this, at omega t equal to beta, it's called the stored energy decreases to 0, and T1 and T2 are getting turned off because of the energy stored in the is getting 0. The T1 and T2 getting turned off, and then the output voltage equal to 0. And during the negative, therefore, until the next firing, the output voltage equal to 0, because none of the CR will be conducting. At pi plus alpha, during the negative cycle, T3 and T4 are getting at the forward blocking state and can be turned on at an angle pi plus alpha degree. And that same thing repeated when T3 and T4, that will be continuing through this path. And even though voltage is 0 here, that still it is our device is continues to conduct. Therefore, this is the output voltage, and this beta is called of course the conduction, and beta is the conduction angle. That is from alpha to beta, it is conducting. Of course, there's a discontinuity is the that is because of but as I told you, if the magnitude of the value of the inductor is very large, then you can make the current continuous, so that it's a continuous conduction mode, it can work. Therefore, this is a discontinuous conduction mode, and the average output voltage can be calculated as VDC equal to 1 by pi integral alpha to beta Vm sin omega t, or it can get as Vm by pi into cos alpha minus cos beta. Therefore, the average value of the output voltage is given by Vm by pi into cos alpha minus cos beta in a discontinuous conduction mode. In this case, we are, rather than connecting an inductance and a resistance, we are connecting a RL load, R resistance and inductance in series. In a single phase converter with RL load, as a previous slide, it was a discontinuous conduction mode, but in a continuous, to make it a continuous conduction mode, one method is you can increase the magnitude of the inductance. If the inductance value is more here, now you can see that one, rather the current is never goes to zero, it is always positive, and that until the next firing, that is positive. Therefore here the output voltage, you can say that one, from pi to pi plus alpha, it is same, it is the gain pi plus alpha, it is comes like this one. Therefore this is the output voltage or the voltage across the RL load, and this is the current through the RL load. This is always the current is positive. There is no zero current as such. Therefore, that's called the continuous conduction. And if you're looking to the current through the source IS here, from here to here, from alpha to pi plus alpha, the current is positive, and from pi plus alpha to again 2 pi plus alpha, the current is negative. Therefore, this is the source current through the source, and this is the load current. All that's never current goes to zero. It's a continuous conduction, and during that period, this is the output voltage. From therefore, in order to find out the average output voltage, it is equal to 1 by pi integral alpha to pi plus alpha. When it was discontinuity, we are integrating alpha to beta, but here you can see that current is continuous, and therefore the voltage is until the next firing of the thyristor, that is T1 and T2 are fired between this alpha to pi plus alpha, T1 and T2 are conducting. From pi plus alpha to 2 pi plus alpha, T3 and T4 are conducting. Therefore here always there is no zero voltage case. Either T1 by T2 or T1 and T2 or T3, T4 are conducting. Therefore, the output voltage is, this waveform is output voltage. And when T1 and T2 are conducting, same as this one, same as this output voltage is same as the input voltage. When T3 and T4 are conducting, since it is here positive, it is just inversion comes here. Therefore, the output voltage is like this one. Therefore, the average value of the output voltage is given by integral 1 by pi integral alpha to pi plus alpha Vm sin omega t d omega t, or Vm by pi minus cos omega t alpha to pi plus alpha. Substituting that one, we'll be getting Vm by pi into cos alpha plus cos again cos alpha, which is equal to 2Vm by pi cos alpha. Therefore, in this continuous conduction mode, the average voltage across the diode in a single phase full converter with RL load, here the average voltage is given by 2Vm by pi cos alpha. 2Vm by pi cos alpha, where alpha is the firing angle, the instant at which it is getting turned on, that's called the firing angle, and Vm is the maximum value of the source voltage, which is equal to root 2 times the RMS value. Therefore, this is average value equal to 2Vm by pi cos alpha. Now we'll be considering a single phase full bridge converter, only. With RLE load. Previously we inductance and resistance considered. Now one more element, that is battery source E. RLE, E is the resistance, inductance, and actually in a DC motor can be considered as a back EMF. Therefore RLE load is there. Therefore this is a single phase supply, T1 and T2 and during positive hour cycle, and T3 and T4 is during negative hour cycle. And here we can say this is a positive, of course, here this will be conducting when it is forward bias, and this will be conducting when these points are reverse bias. Therefore, T1 and T3, and then it's called T2 and T4, and this is an RLE load. Therefore, here during the positive hour cycle, that is from 0 to pi, it's called the positive hour cycle of the input, and from pi to 2 pi, we call the negative hour cycle of the input. During the positive hour cycle of the input, T1 and T2 are in a forward blocking state, or that's forward bias case. And at an angle alpha here, T1 and T2 are conducting, and then output voltage is same as the input voltage, From, you can say that from here alpha, and that will be continuing until pi plus alpha. Therefore, this RLE load that will be continuing until pi plus alpha. This T1 and T2 conducts. Therefore, from here alpha to pi plus alpha, devices or the switches T1 and T2 are conducting, and from pi at instant pi plus alpha, or here at the instant pi plus alpha, what we are doing, we'll be turning on T3 and T4. T3 and T4 are getting turned on. What happens is that when T3 and T4 are getting turned on, here this is a positive voltage, and when it is coming a positive voltage here, once we are giving a triggering pulse here that will be applying a positive voltage here, that gets turned off. Therefore, the T3 and T4 you can say incoming SCR. Already T1 and T2 are conducting. Now we are at pi plus alpha, you are triggering T3 and T4. For T3 and T4 are the incoming SCR. When T3 and T4 are incoming SCR, since it is this voltage is positive during this instant, this is getting reversed. This gets reversed. Where reverse voltage comes here. The same time here, since here this is turned on, that will be applying here. This is also not this. This is getting turned off. For the SCR which is already in conduction T1, and because this is also positive, this is getting turned off. At that type of turning, or that device is getting turned off, and here that's T1, that's called a reverse voltage apply across the SCR which is already in conduction when the incoming SCR T3 and T4 are triggered on. So that this will get turned off, and T3 and T4 are conducting. And when T3 and T4 are conducting here from pi plus alpha to 2 pi plus alpha, T3 and T4 are conducting. Again, the path is through the load current flows like same path. And since because of the battery as well as inductance, the output current is what we are assuming is always constant, steady, constant value of the output current. Again, output current is a steady value, and the output current during the negative half cycle of the input, output current is flowing like this one. Therefore, that is from pi plus alpha to 2 pi plus alpha, and then that is repeating. Therefore, this is the voltage across the load, RLE load here, and the average value of the, if you calculate the average value of the output voltage as we already derived, 1 by pi integral alpha to pi plus alpha Vm sin omega t, or 2 Vm by pi cos alpha. So the average DC voltage of this one is given by 2 Vm by pi cos alpha, and this is the output current, that is always the load current, or through RLE load we are assuming that constant load current is, or output current is constant. And since the during from alpha to pi, the current through the source is positive because current is flowing like this one, will be getting a positive constant current. And from pi plus alpha to 2 pi plus alpha, T3 and T4 are conducting. Therefore, the current is in this direction, the device through this device. Therefore, the current through the source is opposite. That is why you're getting minus I. Therefore, it says square wave. The current is a square wave of this type. Plus, you can set plus I naught from alpha to pi plus alpha. From pi plus alpha to 2 pi plus alpha, it is equal to minus I naught. Therefore, this is the source current, this is the load current, this is the load voltage, and this is the input voltage. And the average value of the load voltage or output voltage equal to 2 Vm by pi cos alpha. In this we can say that from when alpha is equal to less than pi by 2, we can get this magnitude is equal to positive 2 Vm by pi cos alpha. When alpha is less than 2, this is positive, or in that case the output voltage is equal to positive, or AC input is rectifying. In that case, this is working as a rectifier. So for 2 Vm by pi cos alpha, when alpha is less than pi by 2, it is acting as a rectifier, that is rectification. When alpha is more than pi by 2, when the firing angle is more than pi by 2, we can say that 2 Vm by pi cos more than pi by 2 will become negative, or VDC is negative, that is working as an inverter. In that case, actually you need a battery type, the source is required. RLE type load is source is required. A battery is a series with inductance and armature. Load current is continuous. In this case, a battery type load is required. In that, if you are operating this one more than pi by 2, from the source, if a battery type source is there, that power will be going back to the, from the load side, it is going back to the source, or that is, this is working as an inverter. Therefore, when firing angle is more than pi by 2, the power or energy, electrical energy is flowing from the load side into the source side, or this is working as an inverter. That is possible if it is an active source is there. An active source like this is, if you consider in a DC motor, it's a back EMF, this is inductance, armature inductance, armature resistance. In that case, you can reverse, the power flow can be from the motor into the source. Then this is working as a inverter. Therefore, this RLE means a battery with a series with inductance, and or that can be considered armature of a DC motor. Assumption is that load current is a constant, and when alpha is less than 90 degree, this is the voltage is positive, it will be working as a rectifier, that is in this case. And if alpha is equal to 90, the output, the 0, When alpha is more than, it is working as an inverter. In that case, the power is flowing from the RLE load into the source. Now here you can say that when, if you consider the load side here, the load voltage can be either positive or negative, but always the current through the load is always positive. You can say that one. Current flow, always it can flow in this direction only. But the voltage can be either positive or negative. Therefore, it can work as either in first quadrant or in a fourth quadrant. Therefore, this type of arrangement can be, if it is a motor DC type motor, it can operate either in first quadrant operation or forward motoring operation, or it is the, reverse blocking case. That is this one, fourth quadrant. It can be operated in a two quadrant operation is possible here. So for continuing the single phase full bridge converter, when alpha is more than 90, as I already typed, the average voltage equal to 2 Vm by pi cos alpha. If alpha is more than 90, this quantity is equal to negative. 2 Vm by cos alpha is negative, meaning that here, of course, here is negative. Now, if this is a active source as such, just like a battery or back EMF here, the power will be flowing from the load into the source. Then this is working as an inverter. Therefore, when alpha is more than pi by 2, this is working in as an inversion operation. When alpha is less than pi by 2, it is working as a rectification, or it can be either operated in the first quadrant with positive voltage and positive current, or negative voltage with positive current. It can be operated in a fourth quadrant. Therefore, when alpha equal to less than 90, it is positive. It's called the rectification. When alpha equal to 90, the output voltage equal to 0. And when alpha is more than 90, BDC is negative, because from 2 Vm by pi cos alpha, it is negative, meaning that here is equal to negative. Therefore, the power can be flown from the source into the, from the load into the source, or this converter can work as an inverter, so that the power flow is from the load side into the, from the load side into the source side. Or therefore, that is working as an inverter. It's called the inversion operation. That is possible only if it is an active source is here, like battery or a back EMF of a DC motor is there, it can work as an inverter. Now continuing the single phase full bridge converter with RLE load, it's a continuous conduction which alpha is more than 90. When alpha is more than 90, average output voltage, when alpha is more than 90, average output voltage equal to negative, because 2 Vm by pi cos alpha, that is negative, but the load current is continues to flow in the same direction, so the output power is negative. Load current is same, but this voltage is equal to negative, means that the power, if you saw the output power is negative, you can say that output power is negative, or power flow is from the load to the source. Power flow, that is, it's working as an inverter. It is possible only for an active type of load. That is, when the load has an EMF or source of RLE load, that power flow from the source side, the load side to the source is possible only in the case of active type of load. That is to work as an inverter. For operation of the converter lies in either first quadrant or fourth quadrant. That is either first quadrant or in fourth quadrant. That is, voltage can be positive or negative, but current always it is positive. That is either in first quadrant or in the fourth quadrant. For regenerative braking of the DC motor, alpha is made more than 90 degree. At the same time, the armature terminals are interchanged. Armature terminals are interchanged, so that the current flows from the DC machine acts as a generator, and in the AC, and that is flowing to the AC source. A mechanical arrangement is used for the reversal of the connection. Therefore, then the motor terminals change, and then power flow is from the the load side into the source. Therefore, inversion is not possible for a passive type of load. It is not possible. Simple RL load, it's not possible inversion operation. But to make it work as an inverter, there should be an active load like RLE load or like a DC motor. Now continuing the inversion mode, as alpha is more than pi by 2, it is working as an inverter, in which you can say that the voltage here across equal to negative and the current is for negative positive. Therefore, of course the power is negative, meaning that power flow is from the load side into the source. Also called regenerative braking concept is like that one only. When alpha is more than 90, the output power is negative, and the power flow from the load side into the source only for the active load. That's very important. Only for the active load that will be working as an inverter. Therefore, that operation lies between first and fourth quadrant, and connection, in this case, the connection of the converter and DC motor during the inversion. Therefore, here you can say that the connection of this one is to be reversed. Previously, it was here plus and minus, but when it is working as an inverter, the connection is to be reversed. And for regenerative braking of a DC motor, alpha is made greater than 90 degree. The same time, the armature terminals are interchanged. Armature terminals are interchanged, so that it acts as a generator. The current flows from the load side into the source, and inversion is not possible here. Actually, the current, the power flow is from that one, rather than the always current through the load is like this only. But since the power flow is like this, power is flowing from the load side into the source side. So that it acts as here 90 degree. The same time the armature terms are in the chain, so it acts as a generator. Current flows that then current flow, you can say that the power flow is from the I mean or the power flows from the load to source. From the load side the power is flowing, or that is converter is working as an inverter. The inversion is not possible for a passive load, RL type of load. Only for the RLE type of load or active load, the power can be flown from the load side into the source side, or that can work as an inverter. Inversion possible only for a uh, active type of load. When it is working, alpha is more than 90 degree. For if the firing angle is less than pi by 2, it is working in a rectification mode. And when firing angle is more than pi by 2, it is working as an inverter, or the power flow is from the RLE load into the source, provided okay, alpha is more than 90 and it is an active load. In the next presentation, we'll be explaining, or we'll be seeing the analysis of this full wave converter. We'll do the analysis of this source current, and we'll be calculating what is the of course the uh, displacement power factor, what is the distortion factor, what is the power factor, what is the total harmonic distortion, etc. That analysis we'll be doing in the next presentation.